Hey, so this is the last in our series of intermolecular forces, and we're going to focus on dispersion. So dispersion is also known as induced dipole, and basically what happens is that two nonpolar compounds, when they get near each other, induce dipoles on each other. So even though both have even distributions of electrons due to the nonpolar bonds that they have, when they get near each other, the electrons from one begin repelling the electrons from the other, which induces a dipole. Now, as that dipole is induced in one, it actually starts inducing a dipole back to the original one. So for instance, if the electrons of this one start pushing the electrons of that one over, it induces the dipole, moves the electrons over, creating a temporary dipole. However, because this becomes more positive, it starts actually pulling electrons from this one over, inducing a dipole back on the other one. Now, this dispersion force, or these induced dipoles, are extremely weak and temporary. So this is the weakest of the intermolecular forces. And therefore, they are not bound together very tightly, but they are bound together enough that they can actually allow them to stick to some degree. These are also known as London dispersion forces, named after a scientist named London, who, not the city, but a scientist, who was able to describe what would happen. These forces are extremely weak, and so substances that are nonpolar tend to be held together very weakly and are easily disrupted. Many of them are gases at room temperature and have to be cooled down to extremely low temperatures for them to actually stick together. Otherwise, at normal surface temperatures, the intermolecular forces are too weak to hold them together and they escape as gases. Even in the solid stage, they tend to be brittle and fragile and easily broken. So for instance, if you were to take carbon dioxide and you wanted to turn it into a solid, we call frozen carbon dioxide dry ice, you're going to have to cool it down to more than 90 degrees Celsius below zero. So it has to be pretty dang cold. In addition, even though it's a solid, it doesn't form a very strong crystalline structure, and just the light tap of a hammer will cause it to crumble and break apart. There is a general rule, though, that says that the larger the molecule is, the greater its induced dipoles. And this is true across the board, across all intermolecular forces, but is particularly important when talking about nonpolar substances. The larger the molecule is, the larger its dispersion forces. And simply, there are more electrons who can move to more places to induce a larger dipole. So if you take a look at these two examples here, this is methane, CH4. It's going to only be able to form a dipole in these two spots. But if you look at something much larger, like this hexane molecule, there are many more places where these dipoles can be induced, which means that its intermolecular force is going to be greater. That means that they can stick together at higher temperatures because they have more induced dipoles available. Even atoms with the same number of molecules will have higher dipoles based on its geometry. How many places can they go? Which has a larger surface area that allows electrons to migrate and induce these dipoles? So substances that have greater surface area or larger molecules will have higher melting points. So here is an example of a substance whose melting point is 9.5 degrees Celsius, while this one, who's kind of more spread out a little bit, has a higher melting point at 36.1. So molecules will have greater induced dipoles the larger they get. So let's take a look at two nonpolar molecules and compare those properties. So on one hand, we have propane here, which is 3 carbons and 8 hydrogens. All the bonds are nonpolar, and propane is a gas at room temperature. So propane comes out as a gas. If you want to store it, you can put it under extremely high pressure and force these molecules together and turn it into a liquid in a pressurized tank. But if you release it into atmospheric pressure, it's going to come out as a gas. And that's what's happening here. So someone shot a bullet into a propane tank. The propane was liquid inside the tank, but came shooting out as a gas. On the other hand, oil are these long chains of carbons and hydrogens, still nonpolar, but The oil molecules are so much larger that they have more of an induced dipole, more places for electrons to migrate when they induce dipoles on each other, and therefore it can sit as a liquid at room temperature. Still nonpolar, but it's a liquid because of those greater induced dipoles. However, because the oil is nonpolar, it's still not going to want to interact with water very much. Water's polar, oil's nonpolar, so they aren't going to mix together. And so what you're going to see happen is, when you put them together, they are going to separate. What ends up happening is that the water molecules are more attracted to each other than they are to the oil molecule. So the water molecules are going to clump together due to dipole-dipole interactions. And if there's an oil molecule in the way, they essentially push the oil molecule out of the way so they can get together. Think of it like a date in which you have a third wheel. The people on a date really want to get that third person kind of out of the car, out of the way, so that they can get together. That's what's going on when oil and water are put together. It is the van der Waals forces and these dispersion forces that allow organisms and molecules to stick together. For instance, have you ever wondered, like, how does a fly climb up a wall, walk on the ceiling? It is due to intermolecular forces. On the feet of the fly are a number of molecules that are sticking off, and they've got a very large surface area of molecules. And they are using intermolecular forces to stick to the wall. They are using these dispersion forces. They are using dipole-dipole forces to stick to the wall. And as long as the organism doesn't have more mass than the intermolecular forces can hold on to, it is able to support itself. If you take a close look in an electron microscope at the feet of flies and spiders and other insects that are able to climb these surfaces, you will see thousands and thousands of these tiny little hair-like projections, each one of those having molecules sticking off. They want to increase the surface area, have as large a surface area as possible to increase the induced dipoles available. The more surface area there is, the more they will stick, just as it is occurring with these larger nonpolar molecules like oil. Eventually, they would be getting too large to be able to do it. So there's a limit to the size that they can be before their weight is too heavy for these forces to hold on to. Now they want to have just enough intermolecular forces to support their weight, but not so much that they're literally stuck to the wall. They need to have it be weak enough that the muscles in their legs can pull their foot off and reattach it. Now, for those of you who are wondering, is Spider-Man real? The answer is, I'm sorry, no. The intermolecular forces, especially dispersion forces, are far too weak to allow something the weight of a human to stick onto the wall without other mechanisms like suction cups or hooks that physically rip into the material. Just using intermolecular forces, not enough. So then the question is, how big can an organism get to? What is the largest animal that can walk up glass or other surfaces using only intermolecular forces, not using claws and hooks to grab onto materials, not using suction cups, but just using intermolecular forces? Anyone got a guess? How big can you get? The largest animal that can do it are geckos. Geckos have thousands of these molecules attached to the toes, and they are able to use intermolecular forces to walk up surfaces. And they are the largest animal on Earth who climbs using only intermolecular forces. Those are dispersion forces. In our next set of videos, when we look at melting and boiling points, we're going to bring this all together and talk about how the different forces that are available affect the properties of those substances and whether they're going to be a gas, a liquid, or a solid at room temperature. Before we do that, I want to leave you with this thought exercise, and in the next video we will give you the answer to this thought exercise. If I were to take a piece of iodine, which is I2, two iodine atoms bonded together with a single covalent bond, it looks like this when it's a solid. It's a kind of silvery grayish color material when it's a solid. When it vaporizes, it turns purple into a purplish gas. What would happen if I took a piece of iodine and I were to drop it into a glass that contains both oil and water? If I were present in class, I would actually show you this and we would actually see what happens. But I want you to think about this. I take this piece of iodine, I drop it, it goes through the oil, through the water. What are we going to see happen? Will it interact with oil? Will it interact with water? Does it do both? Does it do neither? Think about intermolecular forces, and we'll check it out in the next video.